All right, folks, here we go with the last video of this section on Newton's third law. This is the one that everyone remembers the tagline, but it's a little bit more complicated than maybe you remember it. Newton's third law is the law of action and reaction, and the tagline is every action has an equal and opposite reaction. As it turns out, action and reaction are terrible names because you are already thinking that the action occurs first and the reaction occurs second, but that is not true. So here's what Newton's third law means. The most essential piece of Newton's third law is that forces occur in pairs. Now, it's kind of crazy to think, right, the just size and scope of the universe. At any given time, there are an even number of forces in existence because it is impossible for one force to exist in isolation. There's another way to say this. A force is an interaction between objects. It takes at least two objects, or rather, it takes two objects to have a force interaction. And so because it takes two objects, that means that that means that one force has to act on each object in that pair. So that's like the most important idea. And I just kind of said the second idea. So each force in the pair acts on a different object. So that's really important, and that's really helpful because it allows us to analyze collections of objects and find the commonalities between them. The part about action and reaction that I want to dispel is that these forces occur at the same time, so simultaneously. The action does not precede the reaction. The action and reaction begin to exist at the same time and end at the same time. Imagine like a tennis racket colliding with the tennis ball. There's no way that the tennis racket can hit the ball before the ball hits the racket. That interaction has to start at the same time. And that's really important. The last one is going to make your life a little easier. The forces in the pair are always the same type. Okay, that's actually not the last thing. They're always the same type, meaning like they're both the normal force, they're both the gravity, that sort of thing. And then equal and opposite, the forces have the same magnitude, but opposite direction. Okay, so I'm just going to give you like a really simple example. We talked about the sled, the person sledding on the hill. So I get to draw this picture again, and there we go. The free body diagram for the sledder has gravity, it has a normal force, and it has a friction force. The number of forces you draw in your free body diagram is the number of action-reaction force pairs that exist. So action, reaction pairs. Okay, so we will start with the normal force. So normal. Now this arrow represents the hill pushing up on the sled. Well, there is an equal and opposite reaction force where the sled is pushing down on the hill. there would not be a normal force on the sled if the sled weren't also pushing down the hill. That causes the other force to exist at the same time. Okay. This is the next one's friction. And friction gets kind of odd also. So the hill pushes back on the sled. Okay, that's kind of easy to see, right? The sled's coming down the hill, and friction is pointing up the hill, so friction is pointing opposite the direction of motion. Well, Newton's third law says that the sled pushes forward on the hill. So, in an extreme scenario, if this sled had enough mass, in theory, then this sled could pull the hill forward with enough of a net force on it, in theory. The last action-reaction pair is gravity. This is a really important one to cover because it gets into the source of gravity. It's not the hill. The force of gravity is due to, well, the force of gravity that we experience on the Earth is due to just a really large, massive object that's near us all the time. And so the force of gravity, because it points down, we know, okay, well, the center of the Earth is below us. And so the Earth is below us. So Earth is actually the source of the action force on us. So the Earth pulls down on the sled. So gravity is caused by the Earth, and I left that out of the notes, so now you know that when we talk about Fg and mg, that's the force that the Earth exerts on something. So the Earth pulls down the sled, that's the gravitational force, and then that must mean that the sled pulls up on Earth. And a question that you might want to start thinking about now is, well, they are both pulling down on one another, but the sled is the only thing that is apparently moving, which is true, right? The sled moves a lot. The Earth doesn't move really at all in response to the sledder. The Earth doesn't like speed up or slow down when the sled starts going down the hill. So these two forces are equal and opposite, so why is it that the sled moves so much, but the Earth doesn't move? And I'm going to answer it in just a second, but if you want to pause and try and answer that yourself, go for it right now. Okay, so the reason why the Earth doesn't move, but the sled moves, is because of Newton's second law. If the forces are equal, that doesn't tell you the entire story about acceleration. So the reason the sled accelerates a lot down the hill, but the hill doesn't accelerate toward the sled, is because the hill has so much more mass than the sled. The hill's part of the Earth, so you can think of the hill as having the mass of the entire Earth. So the acceleration of the Earth will be extremely tiny, whereas the sled has a much smaller mass, and so that means that this fraction is going to have a larger value, and so there's be a bigger acceleration. So Newton's second law and third law do a lot of playing together in our concepts and in our calculations as well, and that's Newton's third law.